Hello, welcome to my lab video. Today I'm going to use physics to find the moment of inertia of a marble.
The goal of my experiment was to determine a marble's moment of inertia by finding its potential energy and rolling kinetic energy while rolling down a ramp, and then compare this value to the value found by using the generally accepted equation for a solid sphere's moment of inertia. In this experiment, I conducted 4 separate trials. For each trial, the independent variable was the height of the ramp, and the dependent variable was the final velocity of the marble. My materials for this experiment include a ramp, a marble, a lever with measurements, a stopwatch, an electronic balance, and a tape measure. Here's the procedure I followed for my lab. First, I created my ramp with help from my dad. I used a 24 by 8 inch 16 gauge piece of steel sheet metal for the ramp, and I drilled a small piece of wood on the back of the top of the sheet metal so the stilts I made would be able to prop the ramp up. For the stilts, I used a bandsaw to cut 2 6-inch long pieces of aluminum metal and then drilled 4 holes in each piece with a drill press so that I could hold the pieces together in different positions with 2 bolts to make different heights. I also smoothed the edges and corners of the stilts in sheet metal with a belt sander so that I wouldn't cut myself while doing my trials. Next, I measured the height of the ramp starting from the top of the steel sheet and recorded it in the data table. Then I measured the length of the ramp, which is the displacement of the marble. Next, I measured the marble's mass with the electronic balance and the marble's circumference with the tape measure. At the start of my first trial, I held the marble at the top of the ramp at rest. Then I started the stopwatch on my phone at the moment I released the marble and stopped it once the marble hit the table. I recorded the time measured on the stopwatch and then repeated this twice for the same ramp height. After that, I changed the height of the ramp by removing the aluminum pieces propping the ramp up, unscrewing the bolts holding them together, and re-screwing them into different holes so that they had a different total height. Then I replaced them under the ramp and measured the new ramp height. I used this new ramp height for my second trial, and I repeated the same process that I had followed in my first trial. Then, once I had 3 recorded times, I changed the ramp height twice more and repeated the process twice more so that I had a total of 4 different trials. Now that I had all my data, it was time to begin calculations. In order to find the moment of inertia of the marble, I had to find the total energy used during the experiment. Due to the law of conservation of energy, I knew that the initial amount of energy would equal the final amount of energy. The marble started with only potential gravitational energy because it was at rest and it had height. Its final energy was rolling kinetic energy, which is the sum of its translational kinetic energy and rotational kinetic energy. The equation for potential gravitational energy is mass times gravitational acceleration times height. The equation for translational kinetic energy is 1/2 times mass times the final velocity squared. And the equation for rotational kinetic energy is 1/2 times the moment of inertia times omega squared. Omega, however, is equal to the final velocity over the radius. So the equation for the rotational kinetic energy in this situation is equal to 1/2 times the moment of inertia times the velocity over the radius squared. First, I need to find the final velocity of the marble. And for that, I need the time the marble traveled, the displacement of the marble, and the acceleration of the marble during the trial. For each trial, to find time, I will take the average of the 3 recorded times for the marble. So I will add the 3 times together and then divide the whole thing by 3. So for the first trial, 0.63 seconds plus 0.66 seconds plus 0.66 seconds equals 1.95 seconds. And divided by 3 equals 0.65 seconds, which is the average time the marble traveled during the first trial. Next, I need to convert the displacement of the marble to meters so that we have accurate units for our velocity. Throughout all 4 trials, the displacement of the marble remained the same at 24 inches. In order to convert this to meters, I have to multiply it by 0.0254 meters over inches. Therefore, the displacement of the marble is equal to 0.6096 meters.
After that, to find acceleration, I will use the kinematics equation x equals 1/2 at squared. I will plug in 0.6096 meters for x and 0.65 seconds for t. Then I will rearrange the equation to equal a, so that I have a equals 2 times 0.6096 meters all over 0.65 seconds squared. Therefore, my final answer for A for trial 1 is 2.886 meters per second squared. Finally, to find the final velocity of the marble, I will use the kinematics equation Vf equals V naught plus At. I will plug in 0 meters per second for V naught, 2.886 meters per second squared for A, and 0.65 seconds for T. Therefore, my final answer for the final velocity of the marble for trial 1 is 1.876 meters per second. Now that I have all the values I need, I can set up my total energy equation in order to solve for the marble's moment of inertia. Using the law of conservation of energy, I know that the amount of energy involved in the experiment stayed constant, so I can start with E naught equals EF. I also know that the marble started with potential gravitational energy and ended with translational kinetic energy, plus rotational kinetic energy. Therefore, I can plug these into my first equation so that I have the potential gravitational energy is equal to the translational kinetic energy plus the rotational kinetic energy. Because I also know the separate equations for these three energies, I can plug those into this equation. Now I have mgh equals 1/2 mvf squared plus 1/2 I Vf over r squared. However, even though I conducted 4 separate trials with different data, I will only need to use this equation to find the moment of inertia once, because I will create a graph from data collected during all 4 trials to help me derive the experimental value for the moment of inertia. My graph will be the final velocity squared versus the height of the ramp. Therefore, the slope will be equal to Vf squared over h. I can't get that from the energy equation I set up. However, if I take the inverse of the slope, I have h over Vf squared, which I can get from this equation. First, I need to use the distributive property on the right side so that I can isolate the common factors from the two terms, which is 1/2 and Vf squared. This gives me mgh equals 1/2 Vf squared times m plus I over r squared. Then I need to divide both sides by 1/2 Vf squared. Dividing the left side by 1/2 will put a 2 in the numerator while leaving the Vf squared in the denominator. So the equation will be 2 mgh over Vf squared equals m plus I over r squared. Now the left side has h over Vf squared in it, so when I create my graph, I can plug the inverse of the slope in here along with my other values and solve this equation for the experimental value of the moment of inertia. Now I can use my collected data and calculated values to create my graph. First, I made a final velocity versus height graph to demonstrate the relationship between my independent and dependent variables. The graph clearly shows a strong positive linear relationship between the height of the ramp and the final velocity of the marble. According to this data, as the initial height of the marble is increased, the final velocity of the marble increases as well. Next, I squared all the y values of the first graph to make my final velocity squared versus height graph. This graph also has a strong positive linear relationship, and the slope is 14.82 meters over second squared. The inverse of the slope would therefore be 1 divided by 14.82 meters per second squared, or 0.06748 seconds squared over meters. I can now use this value to solve for the moment of inertia by plugging it into the equation I had derived earlier. So now I will be solving for the experimental value of the marble's moment of inertia. To start, the equation I'm using is 2 mgh over Vf squared equals m plus I over r squared. Plugging in my values, I will have 2 times 0.02 kilograms times 9.81 meters per second squared times 0.06748 seconds squared over meters equals 0.02 kilograms plus I over 0.140056 meters squared. Simplifying the math on both sides leaves me with 0.02648 kilograms equals 0.02 kilograms plus I over 1.962 times 10 to the negative fourth meters squared. Next, I will subtract 0.02 kilograms from both sides, so I have 0.00648 kilograms equals I over 1.962 times 10 to the negative fourth meters squared. Finally, I will multiply both sides by 1.962 times 10 to the negative fourth meters squared. Now, my final answer for the experimental value for the marble's moment of inertia is 1.271 times 10 to the negative sixth kilograms meters squared. Now that I have the experimental moment of inertia, I can solve for the accepted moment of inertia for the marble in order to compare the two values. The accepted equation for a solid sphere's moment of inertia is 2/5 times mr squared. Plugging in my data, I have I equals 2/5 times 0.02 kilograms times the square of 0.0140056 meters. So my final answer for the accepted value for the marble's moment of inertia is 1.569 times 10 to the negative sixth kilograms meters squared. Finally, I will calculate the percent error between my accepted and experimental values for the marble's moment of inertia. The equation for percent error is the absolute value of the difference between the accepted value and the experimental value divided by the accepted value and all multiplied by 100. So using my values, the percent error is equal to the absolute value of 1.569 times 10 to the negative 6 kilograms meters squared minus 1.271 times 10 to the negative 6 kilograms meters squared divided by 1.569 times 10 to the negative 6 kilograms meters squared times 100. Simplifying this, I have the percent error equals 0.1899 times 100. So my final answer for the percent error is 18.99%. Now to wrap up my lab with my conclusions. As I determined earlier with my graph, there is a direct linear relationship between the independent variable, the height of the ramp, and the dependent variable, the final velocity of the marble. In other words, as the initial height of the marble was increased, the final velocity of the marble also increased. I also determined that there was a 19% error in my calculations for the lab, and there are a few possible sources of error in the lab that could have contributed to this. One possible source is the energy that was lost due to the unaccounted friction between the marble and the ramp as it rolled down during the trials. Friction is an external force that goes against motion and therefore uses up energy from the system, so this could have affected my calculations. Another possible error was when I measured the circumference of the marble. The tape measure I used was not very good for acute measurements, and it was difficult to get a precise value for the circumference. This could therefore have led me to record a circumference that was off, which therefore would affect the radius for the marble and throw off my other calculations. A third possible source of error was having to calculate the velocity by hand from other data I had collected. Because there were so many other variables I had to calculate and measure to get the final velocity of the marble, there were plenty of opportunities for a calculations error to occur and give me incorrect values for the velocities. There are some ways I could improve my lab design, however, in order to reduce spots for error. One way is by using a lubricant on the ramp while running my trials, which reduces the friction between two sliding or rolling objects. This would allow for less energy to leave the system due to friction and give me a more accurate answer for the moment of inertia. Another way to reduce error is by using a different spherical object that has a known or standard size measurement, such as a known diameter, that could be looked up without need of measurement. Of course, because this lab was done at home, there were difficulties with being limited to what items were available to use in the lab. One example of this was not having a photo gate to use for measuring the final velocity of the marble, which is what I typically use in a classroom lab to measure velocity during trials. This eliminates the need to calculate the velocity and thus further reduces lab error. Thanks for watching, and I hope you liked my video and my lab.